Roads? Where we're going, we don't need roads.
Rational expressions. Now, rational expressions is kind of an overarching term, meaning pretty much simplifying any type of expression that involves variables. So let's take a look at some of the things that fall into this category. Basically, expanding our distribution of binomials is one of these. So recall that you have that FOIL process. If I'm distributing, I have to distribute each of these terms to everything in its opposing terms. So I'll have 3x times 2x, which will give me 6x squared. 3x times negative 5, which would be minus 15x. 1 times 2x would be plus 2x. And 1 times negative 5 would be minus 5. Once I have those, I can simplify this by combining my like terms, and I simplify it to x squared minus 13x minus 5. Okay, now factoring is basically the undoing of this process, going from an expanded term into a product of terms, which is how factors are separated, always by multiplication. So the general rules in factoring, I would always first check for GCF, that simplify your expression if you could pull out a coefficient or a variable. For a quadratic type, ax squared plus bx plus c, if the leading coefficient is 1, meaning this a value here is 1, you're basically looking for two terms that end up with a sum of the b term and a product of the c term. So for example, in this one, I'm looking for numbers with a sum and product of 1, sum of 1, and a product of negative 12. While positive 4 and negative 3 would be two numbers which multiply to negative 12 and add to positive 1. So this entire expression will factor to x plus 4, x minus 3. Just these two numbers. Where things tend to get more complicated, which is what we looked at this year, was when this a term is not 1, so it's greater than 1, so this coefficient is not 1. You're actually looking for things that have a product of a times c using the AC method. Okay, so now we have two versions of this AC method, and I'm going to go through both of them right below here. I'm going to do them in two different colors so you can tell the difference. Both of them actually start off the same way, which is you're figuring out what their sum and product will be and what those two numbers are. The sum is still the same, it's the positive 1, it's my b term, but the product is now this first times the last, which will, in this case will be negative 20. So let me clean this up so I can still see what my original term looked like. Okay, so it's just that product is now the first term times the last term with the a term times the c term, hence the AC method. Method 1 of this, from this point I have two options of things I can do. Once I've found my numbers, which are clearly here, negative 4 and positive 5, which will add to 1 and multiply to negative 20. So unlike the last one where those are just my terms, I kind of have to do some more complicated stuff. So using the AC method, I can split my middle term, which is this positive x number right here. Oop, lost my marker. So my positive x number right here, I can split that middle term into the sum of these two. So that'll be plus 5x minus 4x and then minus 10. So I brought my two other terms down, 2x squared and negative 10. I split my middle term into these two. From here I can factor by grouping. I have a common factor of x here, which I'll pull out, which leaves me with 2x plus 5. On the second term, I have a common factor of negative 2, which will leave me with 2x plus 5. I now have a common factor of 2x plus 5, so I'll take that out. And when I take 2x plus 5 out of here, it leaves me with a factor of x, and when I take it out of here, it leaves me with a factor of 2. So that is the first way I can use to factor this. The second way is with the three-bridge method. So I'm going to write my binomial terms out right here. So this is my first binomial and my second binomial. And then I need to set up some bridges. So my first bridge, my inner bridge, and my outer bridge. So this is an alternative route in this green that I'm doing, which would take it from once you found these two numbers. Now on my first bridge is just my a term. So my a term is 2x squared. And on my other two bridges are my other two terms, which in this case will be 5x and minus 4x. So the coefficients come from the two numbers we found here, and my middle term has a value of x, which is why I'm putting the x's here. From here I look for, at the end of each of these bridges will be the factors of the terms which multiply to the value on the bridge. So since these two bridges overlap here, what goes in this spot will have to be a common factor of negative 4x and 2x squared. Well, the greatest such common factor is 2x. Well, if I have 2x here, Then on the other end of this bridge would have to be x, so that they multiply to be 2x squared. Well, once I have this value, if this multiplies with this factor to be 5x, I know that this factor has to be a positive 5 in order for 5 and x to multiply to 5x. And on the last part, over here, well, that's the end of this bridge, which is negative 4x. And if this is 2x, this will have to be negative 2 to multiply to that term. So notice that I got the exact same value as I did in the first one, just using a slightly different method. So equivalent ways, whichever one you prefer is the one you can use. There's a few special products as well. The special products here, if you notice that you have a difference of 2 perfect squares, you can use the shortcut method. This will always factor to a plus b times a minus b. So for this example, first, remember, always check for a GCF. So there's a GCF of 2, and I'm left with x squared minus 9. And x squared is a perfect square, and 9 is a perfect square. So this will factor further. So I have my greatest common factor, which is 2. Then it'll be x plus 3, x minus 3. Okay, so that's using my difference of squares pattern. So it saves a little bit of time, so you don't have to go through that whole sum product value. Now, sums and differences of cubes, you have to remember this formula. It's the only way to factor it. So I have my 2 values. Whatever the cubed was, I have that without the cube. And then my second term will actually be symmetric to that. So it's x squared, and then I have the product of a times b, and then I have my second value squared. Now the signs are the same, so it's as a minus, opposite, which would be a plus, and always positive. And the way to remember that is with the acronym SOAP, same, opposite, always positive. The difference of cubes, conveniently, is the same exact thing. A, B, A squared, AB, B squared. And then the signs, again, you can use SOAP to help you figure them out. Same, opposite, always positive. So this will be the same since this is a plus, this is a plus. Opposite, this is a minus, always positive, this is a plus. So notice the only thing that changes between these two are the signs. The values themselves remain the same. So if you were factoring something like this, without the cube would be x, and then the number cube that gives me 8 is 2, so this will be 2. Then I have my first term squared, the product of my 2 terms, and my last term squared, and the signs are the same. Opposite, always positive. Second one, same exact thing. The number times itself 3 times would give me, the number times itself 3 times would give me 8 is 2. We just saw that. And then there's a y. A number times itself 3 times to give me 27 would be 3. So then my first term squared, 2y squared, would give me 4y squared. Then my 2 terms combined, 2 times 3 is 6. So 6y. And my last term squared is 9. Then I have the same, opposite, always positive. So there's my 2 sums and differences of cubes. So we're going to go through a couple of these factoring examples together. It is your job to finish the rest of them for homework after watching this video, or you could pause the video now and work on them. So first off, recall that I should check for greatest common factor. I definitely see an m is common here, but also the number 2 is common. So when I factor that out, I'm left with 2m squared plus m minus 10. So now I'm going to check to see if my second term factors any further. Well, since my coefficient's not 1, I'm going to have to use the AC method. So I'm going to write out my sum and product box. Sum, product. I need a sum of 1 and a product of 2 times negative 10, which is negative 20. And it looks like negative 4 and positive 5 will do that for me. So I'm going to factor this stuff kind of to the side. So I'll have my 2 bubbles. I'm going to do this with the bridge. My leading term is 2m squared. My inner and outer terms are negative 4m and positive 5m. So greatest common factor again between 2m squared and 5m is just m, which makes this 2m in order to get a product of 2m squared. So then at the other end of that factor would have to be a minus 2 in order to get a negative 4, and at the other end of this factor would have to be a positive 5. So this second term factors to this, but don't forget about this greatest common factor. So now I'm going to rewrite everything as a final answer. My GCF 2m, then I have 2m plus 5, and an m minus 2. It does not matter what order you write these two factors in. Typically, you write it with the one with the largest coefficient first, which is why I put the 2m plus 5 first, and then I'll box that as my final answer. Scrolling down to number 8. Now, you could try to do this by factoring with finding the sum and product, but it's actually easier if you notice that 4x squared is a perfect square of 2x, and 25 is a perfect square of 5. This is just a difference of two squares. So we noticed before that this is one of our special products. We'll factor to just 2x minus 5, 2x plus 5, and we're done. Scrolling down to the last two. The first one, I'm looking for something that has a sum of 7 and a product of 1. Well, the only factors of 1 are 1 in itself, which don't add to 7. So there is nothing that sums to 7 that multiplies to 1. So this will not actually factor, and it's what's called a prime term, which is when it has no possible factors. We call it prime. So that's it. The last one, to the 4th and 16. Notice again, this is a difference of two squares, because m squared times m squared would be m to the 4th, and 4 times 4 would be 16. So this will be m squared plus 4 times m squared minus 4. But don't stop there, because now look, we have a second difference of squares. So this will be m squared plus 4, the first term. Recall that a sum of two squares is always prime. And then I'll have m plus 2 times m minus 2. So this looks like it actually factored twice. So just because you factored something one time doesn't mean you shouldn't go back and look to see if it can factor further. Try the rest of these examples on your own. We will address any questions you have on them tomorrow.
Unfortunately, no. It requires something with a little more kick. Plutonium!
Rational expressions. Rational expressions here meaning fractions. So let's take a look at some of these. A couple things to be very careful about is that when you're simplifying rational expressions, you can only reduce by factors. So here's a common mistake. People see common factors of 4, so they go, oh, 4s, I can cancel them out, so this whole thing is just 2x. No, that's 100% wrong. Do not make that mistake. What is actually true is that you can only cancel things that are common factors. So the only common factor between 2, 4, and 4 is the number 2. So I can reduce all the way through by 2's. So 2 with itself would be 1, 2 added to 4 will be 2, and 2 out of this will give me 2. So this actually reduces to x plus 2 over 2. If that seems confusing, you could also think of it in the following way. Factor out your common factor of 2 first. So this will be 2 times x plus 2 over 4. And the only time you can simplify is when you have a product. So a product of these two things make them both factors. So the 2 and the 4 will reduce to over 2. And notice that I'm left with just x plus 2 over 2 again. So applying those to some examples, I'm going to do one of each of these groups, and then I'll leave you to do the other. But before I'm able to simplify anything here, don't just go, oh, x squared cancels out, k's cancel out. No. They have to be factored first. So you must always factor everything. So let's factor this. The numerator, what sums to 4 and multiplies to 3 would be 3 and 1. So this will be k plus 3 times k plus 1. Divided by, multiplies the 1 and adds to 2, is k plus 1 times k plus 1, or k plus 1 squared. Now that I have these factored, I can cancel factors between the numerator and denominator as a common factor of k plus 1, so I'll cancel them both out, and I'm left with k plus 3 over k plus 1. Now don't forget, these k's do not cancel out because they are not factors. They are separated by addition, so I cannot simplify this any further since it is fully factored and there are no common factors, so that is my final answer. So with that in mind, try the second one. I'm going to go down here to multiplying, dividing rational expressions. Recall that you're multiplying and dividing, you can cancel any product, any factor of the numerator with any factor of any denominator. The only thing that you have to keep in mind is that when you have a division, you have to first convert this to a multiplication. So I'm going to rewrite this in factored form and take care of this division at the same time. So let's factor each of these. This has a greatest common factor of 4y, and I'm left with y minus 1. And in the denominator, I have 3y and y plus 2. There's my first term. My second term, I'm dividing, so rather than divide, I'm going to multiply by its reciprocal. So this will actually be times y plus 2 over y minus 1. Well, with that written, I can cancel any factor whenever I'm multiplying. I can cancel any factor of the numerator with any factor of the denominator, any factor of the denominator, any factor of the numerator, and then my y's will also cancel here, and this whole expression actually reduces to 4/3. Now the second one is a multiplication, so you don't have to do any reciprocals, so you just factor each term and cancel as you go. So try that now. Adding and subtracting rational expressions. Before I can do anything with adding and subtracting any types of fractions or rational expressions, I need an LCD, and I need to get everything over that LCD. So notice, in this denominator, if I'm trying to find the LCD, I have to represent each of the factors. So here I have a factor of 2 times 3 times x, and in this denominator I have 2 times 2 times y. So if I get an LCD, or I could look at to see what my LCD is going to be, I need a factor of 2 times 3, which is in the 6, and a factor of x. In here, I need a factor of 2 times 2. Well, I already have one of those factors of 2, but I'm missing one, so I'll multiply on a second, and I need a factor of y. So my LCD turns out to be 12xy. So it's the smallest such denominator which is common between these two numbers. Well, to get a 12xy, I need to multiply this denominator by 2y. And whatever I do to the bottom, I need to do to the top to keep this fraction equivalent. And this one, I'm missing a 3x, so I'm going to multiply that to numerator and denominator. I end up with 5 times 2, which is 10, so this will be 10y, plus 3 times 3, which is 9x, divided by, and since we multiply by the missing factors, this will all be over 12xy. So that's this expression written as a single expression. Where this gets slightly more complicated is when I have binomials in my denominators. Same basic idea. I'm going to need to find the LCD, which is representing every factor of the denominator. So I'm first going to factor these. This is x, the difference of two squares, so it's x plus 10, x minus 10. That's what my first denominator is. My second denominator multiplies to 10 and adds to 11 would be x plus 10, x plus 1. So my LCD is going to need to represent all of those factors. So I'm going to need a factor of x plus 10 and a factor of x minus 10. So I'll have an x plus 10 and an x minus 10. I already have, looking at my second denominator, I already have the x plus 10, so now I also need an x plus 1. So that's what my LCD will be for these two fractions. So I'm going to need to get everything over that LCD. So I'm going to need to multiply on by its missing factors. Well, this is missing on by the x plus 1, so I'm going to multiply this by x plus 1 over x plus 1, my first fraction. The second one's missing the x minus 10, so I'm going to multiply this by x minus 10 over x minus 10. What I end up with is 7 x plus 7 from the first fraction plus 4 times all this, which is 4x minus 40, all over that LCD, all of this stuff. X plus 10, x minus 10, x plus 1. I'm going to combine my like terms in the numerator, so I end up with 11x minus 33 over x plus 10, x minus 10, x plus 1. Come on, pen. There we go. And the last thing I'm going to check is if any of this has any common factors I could factor out to see what I end up with. So there's a common factor of 11, so this will be 11 times x minus 3 over x plus 10, x minus 10, x plus 1. Now, had this factor x minus 3 had a matching one in the denominator, I would cancel it out and reduce, but since I have no matching factors with denominator or numerator, that is as simplified as that's going to get, and that's my final answer. So
when this baby hits 88 miles per hour, you're going to see some serious